Hello, and welcome back to our Scalable Modeling podcast. So now we are in the episode 3. In the previous 2 episodes, we have dived into what is scalable modeling and started with how we should do scalable modeling. So in the last episode, we dived into the temporal modeling, which is basically mapping the system processes to a timeline. And in this 3rd episode, we are going to continue converting this temporal model into spatial model. Like I explained earlier, the system in general is having 2 sides. It has the temporal side, so system is constructed from processes, which are kind of time-based, they flow in time. But the system also has a state, which is tied in space. If we want to build a scalable model, we need to be able to distribute the state, so we need to design the system so that the state can be distributed. And therefore, in this episode, we will continue from the temporal model and convert that into a spatial model that we can then implement. So welcome back, and let's dive back into the modeling.
We are in a point where we will need to move to a spatial representation of this solution idea of these processes. We try to kind of keep the timeline still there, but we need to move things a bit differently so that we can take the space into account. And why we need to do that is that these states of the system, they are the spatial element, like you learned in the last episode. So they need to be connected to a certain space in the world. Like, for example, I have my own state and Jose has his own state, and my state cannot move outside of me. Same goes with Jose. So we need to map these into space, and to remain the consistency of the system, let's say system between me and Jose, we need to exchange information, and it goes over time. Example through events or messages in this case.
Yeah,
But yeah,
it's about this thing we get the whole idea of the timetable, like the temporal part in which events may take place at different points in time, but it also means that the state of each system or process, or even the actors in it, is different also. That's the way I think I get this spatial part. It's like we are at different places, and we need to connect the dots of how we get from here to this other place.
Yeah.
Which I think you're going to be doing that now. You're going to be connecting the dots.
Yeah, exactly. And this is that I can say that this is the trickiest part of this whole exercise to demonstrate. I think when you have the right mindset, you understand the need for temporal and spatial. You understand that the need for spatial is due to the basically laws of physics, that you need to distribute things to make them growth ready, to enable their scalability. You cannot have everything on one machine. That's basically the limitation. And when you understand that, and you understand the main picture, the rules in this one, that is something that enables you to start building the spatial model out of this. But let's do it in practice, so you can see how it goes. So for starting to do the temporal shift, I can make a copy of this. I think I have added some things here already to help me get going. The present logistics is there. I can maybe remove it from here. And the timeline is something that we don't need anymore. And this is my toolbox where I can find my sticky notes where I need it. And we have these 2 external systems that we need to solve the whole case. And these are very much spatial. They exist somewhere elsewhere than our wish management. So this is the starting point. And what I said before, the states are also spatial. So we need to maybe move these things around a bit. So let's start by placing the states into different points. It doesn't matter too much where they are in the beginning. And we start noticing some things. Also, for example, if we check the gets child's wishes, and there is a state child's wishes, we notice that, okay, this probably lives quite close by to the child's wishes. And then we have some events. Child added to a naughty list. I believe that we already have it there as an external event, so we need to convert it internal. We can move that there. Present delivered, it already exists there, so we can already, let's say, take it away and we can place that there. So this is the connecting the dots. This is kind of a solving a puzzle, but we need to arrange everything as spatially instead of timeline. So let's move on. We have child's wishes. In this point, I would be kind of even considering that maybe this space, this state doesn't only contain child's wishes, but it contains the information of a child. So I renamed this as a child. And wish received, this is received from child. So we tend to put the events on the right-hand side, like in this picture. Let's see here. So in here, so we have the commands, and we have the command handler, we have the state, and the events are on the right side. And then we project new states from these events. So we follow this approach. We have a commands, and let's take these policies to side for a while. So when we make a wish, we need a command handler here in between. We can have it as an implicit. We don't need to explicitly have it here, but we know that always between command and state, there is a command handler, which will emit events. So when a child makes a wish, it is either approved or rejected. And the wish received is something that I don't know, do we need to have anymore, because we have a command make a wish. Does it bring us any extra value that we have an event called wish received? If we in any case get wish approved or wish rejected, we can kind of subscribe both of those events and we get the same information from those. So we can just remove the wish received. This means that the wish has been received if it's approved or rejected. We want to cancel the wish. So if we make a wish, and we need to have a common place, common state to validate the cancellation. So we could put the cancel wish also here, and maybe move these events up. We usually try to align these as best as we can. But they don't need to be exact. So this is not like exact science. It's more like a tool for communication. So I believe that now when I'm drawing this picture, Jose is able to follow quite well what I'm doing and keeping track how I do this. And that's the idea, that this is a method of communication. In this point, when we are moving into spatial, it becomes more technical. So usually the technical folks are more involved, asking questions that, hey, how about this corner case and this corner case? How do we deal with those? But now we have this kind of a model. So we have a naughty list. We have a naughty wish keywords. And there's still something. We haven't touched the policies yet. So we should somehow make sure that when the wish is made, we check through all of these policies. So something that we can definitely do in the command handler that handles the make a wish, it can check that the child must not have more than 10 wishes, because this command handler can be fed with the child state and make a wish command, and it can reject the command if there already is 10 wishes. So this policy kind of exists as a command handler of this command. But the child does not know about the naughty list nor the naughty wish keywords. So now we need this special component here, special policy, which is a gatekeeper. So we place the gatekeeper here in front of make a wish, and we also have the make a wish command go through here. So the child, we can also then place the child a bit more left. Its child is basically sending this one and this one and this one. So how does it work now is that when gatekeeper is taking in the command, it has the ability to do queries. So it can actually query the naughty list state and the naughty wish keyword, and it can crust the information of the results into a internal make a wish command. And this way the command handler here between the state and the command, which is implicit, not drawn here, it will have the ability to verify all of these policies because the command contains all the needed information and the state contains the rest that the command doesn't know. So now with this approach, we have enabled the command handler, which handles make a wish command, to check all of these three policies. The gatekeeper is basically just crusting the command with an external information from external systems, from the systems that are not within the same consistency boundary.
So this gatekeeper is like a set of policies, pretty much. It's what filters, depending on the constraints or whatever commands we get. Is this correct?
Yes, it is. So if we check from the once again from this blueprint, the gatekeeper optionally here, it takes in the incoming command. It can consult queries. There are some states which are eventually consistent, and this arrow is red, of course, because we have the problem also now that when we are consulting the naughty child list, it may be that when we have received the answer that the child is not naughty, just at the moment the elf notices that the child is trying to, well, not burn the school, but something less bad, and adding the child to the naughty list. And then the gatekeeper passes the command on, saying that the child is not naughty, and the wish gets fulfilled. So there is the time window, the eventual consistency that may cause problems in some cases. But let's say that in this case, if the child becomes naughty immediately at the same time when the wish is being made, maybe we can still let the wish go through, but maybe we should have an additional policy there which says that if child becomes naughty, all the wishes must be cancelled. So that kind of creates a nice loop that removes the problem. And these are just like, these are not technical policies, they are business policies that are applied in the real world as well. So if we would still be in the letter world where the elves are collecting those letters, it could happen as well. Of course, there is less probability because taking the wish list from a child to the Santa Claus, it takes some time. And if during that time the child is added to a naughty list, in the receival time, the naughty list is already up to date and wish will be cancelled. But these are like real life normal processes. They have these same problems as well. And the only difference is that the computers are much faster than humans. So we need to address these problems a bit differently. But we need to recognize these problems, and that's why there is the red arrow to warn us about the potential problem in the using gatekeepers to do queries. And then it's a bit of depending on the situation, but in this moment, usually the people are pretty aware of these policies. So we can maybe even remove them, maybe add a description sticky note that describes these policies. But most of all, we want to keep this picture as simple as possible. So we don't have the query handlers here either. They are needed, but we only keep these elements that are needed for understanding the logic or the model. And some things can be explicit. So now it looks like this. But we still haven't connected this to the external system. So what happens if, for example, the child is added to the naughty list? So we need to have an internal event. We need to have event handler in between. I don't draw it explicitly, but we have it in here. It takes in the event. It is converting that to an internal event, or just simply it can just simply update. The event handler can just update this list, so we can make this simpler. And by the way, there are two types of arrows in the scalable modeling pictures. The ones that are dash lines, they are asynchronous event passing. It takes time for these events to deliver, and these non-dotted lines, solid lines, they are synchronous requests with a response, queries, or comment sending. So now we have a way to subscribe to the naughty list. The naughty list keyword was a static list that we just write by hand. It's still more manual. No need to automate that yet. Can be done later. But then the present logistics. So let's add it, for example, to here. So when the wish is approved, we will order the present. There will be, of course, the event handler, which will move this, convert this event to a order present command, which goes to present logistics. And of course, Git can cancel the order. There is the async messaging going on there, which is really triggering the cancel order. And then when the wish is fulfilled, we would like to mark the wish to be fulfilled. So we actually want to have the wish fulfilled in here. And command could be something like mark wish fulfilled. And then it was already there, yes. So we can then just make an arrow here. External event is received by an event handler, which is implicitly here, and it is converted to a command to a child, again validated against the child, and then the wish gets fulfilled. What else do we need? Well, if the wish is rejected because of it was a naughty wish, we probably want to report it to a naughty child management. So we could have a event passing going here. Like this. So now it starts to be pretty good. We have a connections to external systems. Child can make a wish, cancel a wish, can see what wishes there are. There's a integration from present logistic, which is making the wish to be marked as fulfilled. And it looks pretty good. So now we have crafted our first version of a spatial model. And let's see, I did do this exercise before, so I have the version that I crafted. It looks pretty similar, it seems.
It's similar.
There is some.
That one just had some added policies, which I mean that makes sense. Like we can add so many different policies in between each command and event. Like for example, that one that you have there was about what was it? Whether the child has become or not, or not. You know, those sort of things, which can happen, right? Like in the system, the way that we interpret data may change at some point in time. Well, hopefully not, but you never know.
Yeah, yes, that's true. It seems that the some things that were lacking in my model is that in this previous exercise I had added explicitly the queries. They are of course good to add. They are done against the views. Could be also implicit. And then what I didn't do is that I added an event handler here. So when the wish is rejected, there are multiple reasons for the rejections, not only the naughtiness. So this can be rejected also because it's because there was already 10 wishes. And I added this event handler here that only if the reason for rejection was naughtiness, then we publish an external event naughtiness detected, which is going to trigger report naughty child function in the naughty children management, and then potentially there will be coming an external event from that service, which is updating the naughty list. And in between here, there is actually a conversion to public events, which is again implicit, but I wanted to put a description to highlight that there is this kind of conversion. So we never publish private events outside of our own context. Yes, so this is the spatial model, and now from the spatial model we can do multiple different kind of versions if needed. For example, we can create an integration diagram, which is hiding the wish management internals, just showing what sort of commands, queries, and external events there are, and how the choreography works between these 3 different systems. So this is something that helps to validate that if the external integrations and the APIs are as good as they can, if there are any flaws in the integration thinking and so forth. So this is one type of a diagram that can be made. And then what can also be done is that some pieces within the diagram can be repeated to make it make this spatial diagram to be more time aligned. So we can try to still push this diagram to be also have a bit of temporal aspects, meaning that we still have some parts of this going along the timeline from left to right. And what I have done is that I have copied the naughty children management to the both sides and done same for the present logistics. So this maybe makes it a bit easier to validate these happy paths and the exception paths against the model. So I can show one example of validating a exception path, which should also be a first-class citizens in distributed systems. So let's start from the child. The child makes a wish. The gatekeeper checks if the wish, if the child is on a naughty list and if the wish is naughty. It adds those bits of information to the internal make-a-wish command, which is carried to a command handler, which is actually an implicitly here. And then the command handler validates this command against the state. And it got the information in this case that the wish was naughty. So what happens is that wish gets rejected. So this is the event which is emitted. And then this will be causing the naughtiness detected event in the naughty children management. And maybe probability is quite high, at least if the wish was a flamethrower, that the child gets added to a naughty list by the naughty children management. So this event will be published and the child gets marked naughty. And when the child becomes naughty, this event is updating the naughty list. So there's no direct integration from the naughty children management to this list, but this list is actually internal. And the extra good thing we get from this is that the child also knows if it's naughty itself. So it's questionable, do we ever even need the naughty list here anymore as the gatekeeper as gatekeeper validates the naughtiness from here, because the child already knows itself if it has been naughty or not. But we can still remain it as it is, because the gatekeeper can kind of optimize it a bit, that it doesn't even consult the child if it sees from this list that the child is naughty. So this is optimization that probably should even be removed, and the gatekeeper would only check the naughty with keywords in this point, but it's here. These are the discussion points that we discuss with the other technical folks and business folks, that should we have it this or that, and there are lots of different ways how you can solve the problem. This is just one of the examples. So
I guess,
now
I guess one can argue that you can like add an extra policy there, or like a double check one that has previously been used. I mean, it will be a bit redundant on the long run, but I guess some systems might require that. But yeah, I see what you mean.
Yeah, and the kind of the great thing that I see in this kind of discussion over this, which is the what in the why, what, how model, is that the iteration is really fast. But if we don't do this kind of pictures and we just implement the first idea we get, and then it is decided that, okay, let's not, we don't need this. It doesn't make sense to have it. Let's just move it like this. So I did it in like maybe in 5 seconds. But if you would have coded it already, you would need to spend at least 100 times more time for this change. It's pretty easy to remove code, but it's pretty easy to remove 2 sticky notes and few arrows. It's much more faster. And this is just one example, easy example. There are these examples where editing the chart versus editing the code is much more cheaper than this example. And one more picture to show. I have been talking about these implicit and explicit policies here. So if we would add all the implicit policies as an explicit policies, the picture would look like this. So now all the policies have been added. So when internal event is emitted, there is an event handler that will publish an external event. There are command handlers after every command, query handler after query, event handlers taking in the external events, converting them into commands to command handlers, the gatekeeper and the event handler here. So the technical oriented folks can create this kind of an explicit picture in their heads from these pictures when they follow this diagram. It basically tells where do we need to have policies. So this is much easier to digest for the domain experts. We don't need to have all of these policies in place in the diagram to make also editing the diagram faster. Yeah, so this is kind of, I guess, the end result that we will be implementing and showing the implementation in the next episode. Before ending for this time, I could just do one more extra visit.
A brief recap.
Yeah, and show about the TDD approach that this model also makes pretty nice. So we can use behavioral driven test methodology here and test basically all of the components with that. There's like a one example, for example, that when we have iterated the first model, there's a new requirement that appears, and we can give that requirement with this given when then notation. So given that the child has approved wishes, when child is added to naughty list, then approved wishes get rejected. So this was what we discussed earlier in some point, that we want to add a special case that when child already has wishes and then something that the child is detected to be naughty, we want to cancel all of the wishes that the child currently has. So this is a extra requirement that can be given in this given when then format. We can create a behavioral test for that, and then we can adapt the model to address that. So to adapt the model to address that, we basically add the mark naughty here, and then when the mark naughty is command handler validates it against the child state, it will cause became naughty event and wish cancelled event for all the wishes that the child currently has. And another example of given when then is that they don't need to be all doesn't need to be events like in this case, but we can also have a given when then that given child wished naughty wish event, when make a wish command is received, then wish is rejected. So this kind of a requirement means that also if there is a case that a child creates a naughty wish and immediately after creates a decent wish, there is the eventual consistency problem that if the child gets eventually added to the naughty list, this second decent wish may go through, but this requirement says that it must be rejected. So we sometimes need to also verify these eventual consistency cases, kind of highlighted by the red arrows in the blueprint, and be extra careful to check if these conditions are already also fulfilled in the eventual consistency cases. So basically, idea here was just to highlight that the given when then is really good way to do tests for this, and when you get used to doing these scalable CQS architecture implementations, it's a nice way to even start the implementation by first defining those tests and then doing the actual implementations. All right, but I think we have reached to the end of this time. As a summary, we started from a why in the actual, and now this is like a 2 layers, why, what, how, because last time we discussed about the why and what in the context of scalable modeling. And this episode, we discussed about how we do scalable modeling. But then when we dive into how we do scalable modeling, we actually are starting again with the why, what, how. So the scalable modeling applied, when it's applied, it's also applied in the same way. So first, we discussed that why the solution is needed. Well, the huge volume of wishes and the changing desires of children in their wishes. And then we moved into what, which was the most part of the episode. We created this model, first the temporal, then the spatial. And then the next episode will be that how do we actually implement that conceptual model. Yes.
All right. Thank you. Yeah, I see that we went over all the building blocks that make scalable model successful. So I hope we can get to see them in action in the next episode. Thank you so much for this presentation, Simo.
Yeah, thanks for hosting it.
Right. Thank you everyone for watching this episode that we had today on the scalable models and how we get to provide a solution for Santa on his wish management system. On the next episode, what we are planning to do is we have created a concept application for the wish management system, and we'll be demoing that, and we'll be going over the architecture and the design that took place when we were writing that code. So yeah, please join us, and thank you for being with us today.
Thank you.
Bye.
Bye-bye.